Hi everyone, welcome back. In this video, I wanted to make a tutorial on GSG probes, ground signal ground probes that I used widely for testing different chips. And even it doesn't have to be just integrated circuits. You can also test different substrates, things like that. So I'll show you three different models, starting from a very simplified version to a more practical version, and finally to a more complicated version. So I'll do it all from scratch so that you can, if you don't have any experience in HFSS, you can just follow this tutorial and you should know how to go about it. Okay, so I've just opened HFSS and you should basically open with this. I just saved this GSG probes, this project with this name. Okay, so what we'll do is click on project, say insert HFSS design. And I'll call this, so first we need to make GSG pads on chip, right? So I'll show you how to draw those. Okay, go to HFSS solution type, make it model, driven model. Okay, let's start drawing it. All right, so if you have some experience in drawing structures, on-chip structures in HFSS, you can maybe skip this part to where I start actually designing the probe itself. But if you don't, then I also recommend watching a previous video of the series on which I talk about how to draw inductors so you get some experience. But if not, just follow this, that's fine. All right, so first we'll draw the patch, the pad, I guess, the RF pad. Okay, so I'll call this RF signal pad. Signal pad, set the material to, I'm just using traditional materials here. I'm not using any custom materials, but if you have your own PDK, you should, there are ways in which you can extract the different material sizes and conductivities and so on. I will cover that maybe in a separate video. But for now, I'll just use copper, let's say, or aluminum since it's the top layer, maybe. Sometimes it's aluminum. So let's say aluminum. Okay. And then let's give it a nice color. I know aluminum is not yellow, but I like yellow. So let's go with yellow. Okay. And then we'll go in here and I'll call this, give it some dimensions. So this is the location, pad width divided by 2 minus pad length divided by 2. And then we'll call this, let's say you're making the pad between, let's say you have 9 metal layers and 1 aluminum layer, which is somewhat standard, I would say. Or 5 metal layers can be, it depends on the PDK. So let's say in this case, we have 9 metal layers. I'll make the pad from M9 to the aluminum layer, right? You can also do it from M5, but then you have to keep in mind the capacitance changes. So since it's an RF pad, it depends on your DRC rules, things like that. In this case, just for argument's sake, I'm just making it M9 to, with the M9 and aluminum as a single layer. So the starting would be at M9 elevation. So let's say the pad width is 50 microns, pad length is 50 microns, and aluminum, the M9 layer elevation, I'm not using any standard values. I'll just say it's 3,000 nanometers. This is an arbitrary value. You have to go through your PDK and find the actual value. X size is pad width, Y size is pad length, and Z size is M9, M10 thickness. So the thickness of both M9, M10, and the via between M9 and M10. So you have to keep that in mind. And for this, I'll just say this is 5,000 nanometers. These are again arbitrary numbers, but you get the idea. So there's our pad. It's at some elevation and it's a square pad. And again, the size of the pad also depends on your PDK and what you have available. But for now, I'm just using this. Okay, then what we want to do is we want to make copies of this for the ground pads. Excuse me. So I'll say right click, edit, duplicate along line, and then I can hit F4 That'll give me this dialog box. And here I'll say pad pitch. Excuse me. I'll make the pitch 100 microns, which is also standard, I would say. So this is one ground pad. Maybe we can change the color a little bit. And then we'll say edit, duplicate, mirror, and then hit F3 to remove that dialog box so you can do it manually. Yes, I'm going to click here. Triangle means it's the center of a line. So I'll click here, then hold X, and then move it this way. So that mirrors this pad in X. Okay, now what we want to do is we want to make a ground plane underneath all of this. So let's do that. I'll make another big square. And then let's go call this, I'll call this the bottom ground. And then material, let's make this copper. Again, you have to go through your PDK and see what materials you have, and maybe I'll cover how to do that in a separate video, but yeah, I'll just say copper for now. And then let's give it like an orange color maybe. Okay, and then go in here, minus ground width divided by 2, minus ground length divided by 2. And this will be, let's say, from M1 to M2. So I'll give it the elevation of M1, which I'll say is maybe 500 nanometers. Again, give me some arbitrary numbers here. Oh, sorry, I think I set the ground value width as 500, but that doesn't matter. We can fix that. 500 microns, let's say. And M1 elevation was 500 nanometers. Ground width, ground length, oops, ground length. And I'll say the thickness of the ground is from M1 to M2. So M1, VF1, and M2. I'll say that is around 500 nanometers as well. Arbitrary. For now, it's good enough. So of course, we need to fix the ground width, which I set to 500 nanometers, but we want to be 500 microns. Okay, that's good. So we see that we have our ground plane now underneath it. And if we click on Orient X, this is what it looks like. So there is some space between them. Okay, now typically the GSG pad is at the edge of the ground. It's not so far in. So what I will do here is I'm going to hit F to select faces and then drag over the screen so it selects this face. And then I'll say right click, edit surface, move faces along normal, minus ground length divided by 2, which will bring it back to the center. And then I want to add some spacing. So I'll say plus pad length divided by 2 plus a buffer of 20 microns. Okay, so you can right click, measure its position from here to here. The Y should be 20 microns, which you can see on the left there. One more thing, I guess, is we can change the units to microns so that it's more easy to read numbers off of this. Okay, so this is essentially a good starting point. So let's see how we can go from here. Okay. Next thing I want to do is I want to make a microstrip line that connects to this pad, the center pad. So let me call this actually ground pad 1, and this one ground pad 2. Okay. Now let's make a microstrip line. So what I can do is, again, same thing, just make a square. I'll call this center line maybe. And then we'll assign material as copper. Okay. And then I want to change the color to maybe yellow as well. Actually, since we've used copper, let's keep the color consistent. Orange. I don't know, maybe that's a different orange. Maybe it's this. Okay. All right. And then we'll change the sizing and stuff. Minus line width divided by 2 minus. So actually, we want to start it at the pad, right? Pad length divided by 2. And I'll make this an M9 layer. So M9 elevation. So we'll say it's maybe 3 microns. Line width, line length. I'll make it 10 microns for now. And then we want this thickness to be only M9 thickness. And I'll say that's maybe 3000 nanometers. Okay, so we see our line here. It's attaching to the pad. Right, and the pad, of course, is M9 and aluminum, but the line only is in M9. Let me increase the length of the line. Let's make it 50 microns. Okay. And the ground length also we can actually reduce to maybe 200 microns. Or let's make it to 50 microns. All right, so this is a nice microstrip line connecting to patches. Before I move on, I would like to maybe make it a grounded coplanar waveguide, because that's usually a better line to use. So I want to make, I mean, if you don't know what a grounded coplanar waveguide is, you can look that up. But essentially, it's like adding sidewalls to this line and also to the center patch. So instead of doing it manually, there's a trick that you can use, which I'll show you here. So let's just say I use these 3 surfaces, maybe even this one. Actually, wait. So first what I should do is I'll click F to hit faces, click on this top face, right click, edit, surface, move faces along vector. And I want to move it up all the way to M9 layer. So I'll click here. And then I want to move it, let's say, to the height of M9, which is out here, right? I can directly click here and it'll only go up because the surface cannot move diagonally. So you see that now the ground has reached all the way there, right? But now we want to make a cutout for this line and this patch. So let's do that. I'll hit this face, click on, if I click this face and hit Control B, then it goes to the bottom face. Again, click this, Control B, goes to the bottom. Click this, Control B, and then right click, edit, surface, move faces. Actually, no, right click, edit, surface, create object, unite these objects, then right click, edit, surface, thicken sheet, and I'll say grounded coplanar waveguide gap. So let's make the gap 10 microns for now. We'll correct these numbers later. So you see I've made a gap there, right? Then I hit Object O for selecting object mode. Click on this, Control, click on this that we've just made, and then subtract. So now you see we have a nice, yeah, we have a nice, actually, no, there's a mistake. Yes, so the mistake is that I also need to select the bottom face of this pad. And right click, edit, surface. Okay, so we need to do 2 things. So I'll do the same thing again. Let's say I click this, Control, click on this, and then say subtract, okay. But now you see that like the ground is touching this bottom pad, right? Bottom of this pad. So what we need to do is we'll make a copy of this pad, Control C, Control V. And then I will hide this and then just look at the copy and then hit this. So now we only see the copy of this pad, right? Hit F, control back. And then I want to move this by how much the gap was between M2 and M9 elevation, right? So I'll say move faces along normal, 5 microns. Okay, how do I know it's 5 microns? Actually, I don't think it's 5 microns. So let's see. We say edit surface, move faces along normal. And we want to move it down by the difference between M9 elevation minus M1 elevation minus M1, M2 thickness, right? So let me make clear what I've done. So let's click on this. I'll make this transparent. And then we'll say orient from Y. Okay, so now you see what I've done, right? I've made this gap here. I made that one patch basically is this, and then the other patch is going all the way down. And this second patch is what we want to subtract now. So let's select the other patch. Let's select this. I say subtract, but of course we want to subtract the bottom ground, the signal pad copy from the bottom ground, right? So once you do that, now you see what's going on. Okay, so now we have the ground separated from the patch, but of course we need to move these walls out. So I'll say edit surface, move faces along normal, minus GCPW. Yeah. Okay, done. So now we have a nice cavity, and inside the cavity is our patch, right? And here it's okay for these pads to touch the ground because anyway, it's all connected. So that's fine. And the next thing we need to do is we need to do the same thing out here. So I'll click on this surface, right click, edit surface, create object, right click, edit surface, thicken sheet. And I can call this GCPW gap. And I want to move it negative. So it moves out. That's good. I can click this object, click the ground, click these two things that I've just made, and then subtract. Okay, nice. But again, the issue is that, this is touching the line. So a simple way to fix that now that we have this cavity is hit F, click on this surface, right click, edit surface, move faces along vector. You can click this and then click this. Done. So now we have a nice patch. We have a ground plane connector line, center line, and they're all surrounded by this ground wall. Next thing is we want to move. So I click surface, click this, edit surface, move faces along normal, minus GCPW. Yeah. Okay, that's good. Now we have basically, copper ground plane, copper center line, and 3 patches, which is good. Okay. So I want to change a few things before we assign a port. So I want to change, let's say I already simulated this in the past. So let me just measure the sizes. So this should be measure edge. Yeah, 7 microns is good. 7 microns is good. Measure edge. And the line width that I had used earlier was measure edge 3 microns. Okay. So what I'll do is we will make a port now. So I want to make a wave port because this is a transmission line. And if you don't know what wave port and lump port difference is, then there are other videos out there, and I might make one in the future. Let me know if you want that. So this is a shortcut with method of making a wave port. So this is how I do it. Hit this face, edit surface, create object, edit surface, thicken sheet, minus port cap. So it needs a PC backing, and I'll make that port cap 5 microns. This should be plus port cap, sorry. Now I'll maybe just make it 2 microns. Okay, that's good enough. Then what I'll do is click the bottom surface. So I hit F, click that surface, Control B to go to bottom, edit surface, move faces along vector, hit that, hit that. So now it's touching the ground plane. And then we want to extend these 3 walls. So I'll select those 3 walls, edit surface, move faces along normal, I don't know, 50 microns maybe. So that makes a nice port face. Okay, and we also need to cut this ground so they don't intersect. So I'll say face, click back, edit surface, create, edit surface, thicken sheet, maybe by 20 microns. Now this time I had to go backwards actually, minus 10 microns. And then I'll subtract the ground from this. Okay, so now we have a nice ground port cap that is touching the line. And the nice thing about this is when you change the line length, everything moves. Right, so if I change this to 25 microns, it all moves because we made it with respect to that face. That's why I like to do it like this. Then hit F, click right click, edit surface, create object, edit surface, sorry, not surface, assign excitation, port, wave port. You should see this. And that's okay, you don't have to set anything, just say edit finish. And then this material we will reassign to PEC, which is perfect electric conductor. Okay, that's good. And we can change the color of this. It's not copper anymore. So also the color of this, maybe we can change. All right, so there's your port cap, right? Okay, so now we've added all the metals, so we need to add some dielectrics. The way I usually like to do this is I'll just hit F, select the bottom surface. I mean, if you're using your PDK dielectrics, then you should set them up separately with the right elevation, thickness, and dimensions. But here I'm kind of cheating because I don't want to use any actual PDKs numbers, but you can replace them for that. So what I will do is I'll select this face, say edit surface, create object from face, edit surface, you can sheet by oxide thickness. And I'll set the oxide thickness to 4,000 nanometer, 3,000 nanometers. Okay, we need to extend it in the backwards direction. And maybe 3,000 is not enough. Maybe how about 5,000? That's not enough. So, okay, let me see how to do this correctly. So I want to make it the thickness of the metal that we made. And if I remember correctly, that was 5.5. Okay, so let's make this 5,500 nanometers. Okay, that's good. And then I'll select the face again, edit surface, create object, edit surface, thicken sheet. And I'll say this is nitride. So the top layer is usually like nitride or something like that. So I'll just call this nitride layer, thickness, and this can be 1,000 nanometers. Again, it's an arbitrary number. You have to decide for yourself what you want to use for that. Okay, so let's rename these 2 layers that we just made. Not this. So I'll call this nitride layer. And I can say right click, assign material, and then just choose nitride. I don't know which exact nitride it is, so maybe I'll just say, Actually, it should not be nitride, my bad. It should be passivation. The passivation layer. Nitride is at the bottom. So you have nitride at the bottom, then oxide layers, and then passivation on top. So I'll call this passivation. And then the thickness of this, I mean, I've called it already nitride thickness. I don't want to change the variable name. Maybe I'll make this 3000 nanometers. Okay, so now it covers everything, right? That's good. We need to change the material, of course. So I'll change this to, actually don't know what exactly the material is. So I'll just call it silicon dioxide for now. Let me actually go check what the material is. Just give me 1 second. Okay, just for simplicity, I'm just going to use silicon for now. But if you have your PDK, you will have the right, you should have the right material from that. Okay, so the other ground that we made was this one. So I'll also rename this to oxide, and material also should be changed to silicon dioxide. And then let's make these two colorless, maybe gray, and then turn up the transparency to 1. All right, so I think now we've done the materials, we have the metals, we have the dielectrics, we have a port that's assigned, and then we need to assign an open region. So right click, create open region. Let's run this at 100 gigahertz. So that should create this open air box around. Close this, go in. So to go in, I hit Control D. Okay, so let's check our materials. Aluminum, 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 that's good. Bottom ground, let's look at it. Okay, that's right. Center line is good. Copper, PC backing. We can call this port cap. Silicon dioxide layer, passivation layer above it, and radiation box. Okay, and we have a wayport assigned. So I'll right click here, hit design settings and say enable material override. And then there should also be silicon underneath this. So let's also maybe make that. Edit surface, create object from face, edit surface, thicken sheet, minus silicon thickness. And it can be anywhere from 200 to 500 microns. So I'll say 250 microns. Of course, it should be this direction. So that's your silicon. We'll assign material to this. Silicon. Hit OK. Change this to silicon. And the color is fine. Okay. So there we go. I mean, obviously, in reality, your chip would be not just this. You would have stuff out here. But right now, I've just stopped it at this. And if we want, we can always extend the ground length on one side, I guess. On this side, you can also extend. Oh, sorry. Yeah, the chip should be on this side, not that side. So this looks fine. Okay, in order to figure out what the dimensions of this waveport should be, one way to do it is to simulate it and look at S parameters, increase the size, repeat it, and see if it doesn't change. There are also some rules of thumb that you can use. So for example, the width should be like 10 times the width of this. Height should be maybe 8 to 10 times the height of the substrate and things like that. But practical approach is to simulate it, check that it's big enough. And it should be big enough so that the S parameters don't change for it to work correctly. So let's set up an analysis. I'll say I'll simulate at 100 gigahertz, maybe 20 passes, 2 converged passes. You can play around with these numbers, but it's good for now. Hit OK. Let's say we simulate from 550 to 150 is fine. 401 points. And it should be good to go. Okay, seems like there's a mistake. Bottom ground and RF ground pad. Oh, these two intersect, I see. Because we've assigned different materials to them. So what we can do is we can click on bottom ground and these two, make them visible. And then I'll subtract these two from the bottom ground, but I'll also clone them so they don't disappear. Right, so now we have basically this as the ground. So you have a nice ground, and those pads are sitting inside that ground. Okay, so let me hide these and then say validate. Okay, it's good. So we can run the simulation. Once it's done, I'll come back. Okay, so once the simulation is done, we'll plot some results. So hit right click results, create solution data report. And then we can look at S parameters, for example. S11, of course, it's close to 0 because most of it is reflected back from this pad. It's not like this can radiate at 100 gigahertz or anything like that. But what I care about more is the port impedance. So port Z0, real and imaginary part. So this is actually, since we've used a wave port, this is actually the line impedance of this GCPW line. Right, so it's not exactly 50 ohms, it's between 40 and 50. So to make it 50 ohms, we can make a few changes, I guess. So what we can do is we want to increase the impedance. So we want to make this a bit thinner. So maybe I'll tune this a little bit and come back. But essentially, I just want to start with a 50 ohm line. Okay, so once we've changed it to 2 microns, it's very close to 50 ohms. I'm sort of happy with this. Don't need to tune it anymore. This basically completes our sort of our pad design, right? So I'll save this. And then let's actually go into the probes. GSG probe version 1. Okay, so how do we want to simulate the probe? If you actually look at the probe design, it has 3 pins that come and land on this pad. And then you have to kind of press it so that it slides on the pad, and you'll see some scratch marks, things like that. I mean, how to land a probe is a totally different topic. I don't want to cover that right now, but yeah, essentially there are 3 pins that land onto this. So typically the way it's simulated is they use a structure that looks like this. So I want to make it in XZ. So I'll set that, draw it like that. And then we want to make the Z height as probe height. Yeah, I'll make this 50 microns for now. It depends actually on what the pin heights are. Different probes are different. Different frequency probes are also different. So you need to look at that if you have a data sheet. If you don't have a data sheet, 50 to 100 microns is a good number to start with. So let's make it 75 microns to be more conservative, I guess. Okay. So then what we'll do is I'll copy this, duplicate a long line, click here, hold down the X button. So it only moves in X, which is a trick. And then hit there, click OK. And then right click, edit, duplicate, mirror. Click on this, hold down the X button and mirror it. All right, so we have that going. And then the next thing we want to do is make a bridge between the ground pads. And then I'll make this, I don't know, 10 microns or maybe 25 microns. Okay, so now we have this kind of towering structure. Then we'll click on these 3 and unite them. And I'll assign boundary perfect T. So that's all one metal. And we'll assign a lumped port on this. Port, lumped port. Hit next. Click on new integration line and you can go from up to down or down to up, doesn't matter, it just changes the phase. Renormalize to 50 ohms. Okay, so that's it. That's the simplest way to make a GSG probe a GSG probe. So let's run this and see what we get. Okay, simulation is done. Let's plot it. So I would like to plot S21 and the reflection coefficients. Okay, so we see that, it's sort of matched maybe down here, a little bit below 50 gigahertz. It's not a very good transition. And there are many reasons for that. I mean, it depends on the height of this gap that you left here, the RF capacitance of this pad and things like that. So you can tune that um, to make it work. Alternatively, of course, you can calibrate all of this if you have a TRL calibration of some sort on the chip itself. But it's just to show you how to simulate it. Okay, so this is the first design. It's a little bit kind of crude because if you look at this port, the electric field, the way it is going down this way, right? And it's uniform over this entire thing. But that's not actually how the electric field of a probe comes in. Um, Slightly different. So let's simulate a more accurate version. So I'll call that version 2, copy paste. So this should be version. Okay, let me save this. I had made a version 2 and deleted it. That's why it's complaining. Okay. All right, let's Control D, go in. So what we'll do is we'll delete these for now. Okay. All right, so what we want to do is we want to make something that looks more like a probe. So maybe a cylinder like that. And I'll call this the probe height. And radius, of course, you can make it whatever you want, depending on the size of the pins on the probe. Again, we'll make 3 copies, edit, duplicate along line, along X, and then we mirror it. Okay, and then we'll make all of these copper. Clear this. And you can give it a different color, I suppose. Since we're using copper, let's actually, I want to change the color to maybe something more like steel. All right. Now we want to make an excitation on these pillars. So this is supposed to represent like the probe tips. Can make it smaller, in fact, maybe like 50. Yeah. And then we will assign something like this. Okay, so I'll make this minus 20 microns. I guess the radius was 10, so minus 20. And then I'll also make this the same height as the probe, but negative. Okay, and then we'll make 3 copies of this. Edit, duplicate along line. And let's duplicate it in X this way. Hit OK. Edit, duplicate, mirror, same game again. Hit X, mirror to the other side. And then, like how we did last time, we'll make cap for all of them. And we can make this cap a bit smaller, I suppose. Okay. And then we'll again unite these 3 layers. So you essentially just turned it to the side. Right, again assign boundary, perfect D, and then assign excitation port, lump port. And then we set an integration line this way. It's finished. Okay, so now this is somewhat more realistic because you have these pins that come in, maybe a bit smaller, I don't know, but the electric field now would be horizontal, which is a little bit more realistic. So there's a probe comes in, the electric field is somewhat horizontal and then lands on the probe with these pins. So let's see. Okay, it's complaining about this. Oh, I see. Okay, so it's saying that I'm intersecting these pads. So what we can do is move all of this up, edit, arrange, move them the height of the pad, and then make sure they are touching, right? Okay, it's good. So now it should be clean. Run it. Okay, so simulation is done, and this is what the result looks like. It's very similar to the previous case. We can compare the two. You can see there's almost no difference. And that's fine. These are very similar models, of course. But this is, I would say, more accurate. So if I was you, I would probably be using this one. And this is the model that I prefer the most. At higher frequencies, if you also care about phase, things like that, this becomes more sensitive to the modeling. But you can use either one, really. One more thing I'd like to mention is that keep in mind that if you're using this model, this is just to simulate. The best way to get rid of probe effects is to have a calibration standard on the chip itself, like a TRL calibration on the side if you have the area for it. If you don't have the area, then you can try and do some kind of modeling like this and then de-embed the probe effects. You can also use a calibration substrate on the side, but that'll be different than the chip. So that'll calibrate the probe, but it might not be the same calibration as what you would have, for example, on the chip, because that would also calibrate out the pad effects. Calibration substrate may have different pad sizing and things like that. So, and different substrates. So that's a separate topic. I don't want to get into how to calibrate these probes correctly right now, but this is just to model and draw these probes. Okay, next what we'll do is we'll make a third version, slightly more complicated. Of course, you can take this to the next level and keep going to version 10, where it's exactly the 3D model of the probe and everything. But that's kind of overkill. I don't want to do that. So this is just to show you how you can maybe draw stuff, maybe draw probe design. You can use it as an example of that. So we'll delete these, and then all I want actually is these three. Okay, so now what I will do is I want to make a coplanar waveguide. So let me actually draw that. So center line, let me call it. And we'll make this maybe copper or gold, whatever. And I want to make this color gray. Center line width divided by 2. Center line length divided by 2. Well, actually, let's just keep it at 0 minus center line height. Okay, and then the width measure, let me just measure it quickly. Okay, so I'll make this 0.1 millimeters, 100 microns, 5 millimeters. Well, the center line width. Line length. Let's make this 250 microns. Well, let's make it 1 millimeter. And this will be center line height. Okay, so there we go. I thought I changed the color. Huh? Why is it not letting me change the color? Let me figure this out 1 second. Okay, so I had basically materialized appearance checked, so it doesn't let me change it. But now it should be fine. And I wanted to Set this to kind of like a gold color. Okay, this is a bit long, so I'll reduce this to 500 microns. Maybe that's too long. 250 microns is good enough. Okay. Then I want to make, again, 3 copies. Yeah, apologize for the construction sound. There's some construction going on around here and I can't really do anything about it, but okay. So let's make a copy here. Say, okay. Actually, this should not be 100 microns. This is the gap, probe gap. So probe gap should be let's say, I don't know, center line width plus 20 microns. Sorry, I'm just trying to measure it on a different screen. 25 microns, okay. All right, and then I'll make a copy of this, mirror it in X. All right, so then we have these 3 metal pieces now, basically. And what I want to do is I want to rotate them, edit, arrange. Let's move them first. Maybe by, so I hit click Y and then I move them to the side. And then edit, arrange, rotate about X by minus 45 degrees. So there we go. It looks something like that. Then maybe we can move it along this line to center it. There we go. Okay, so now this looks more like a probe, I would say, a little bit more. We need to connect these. So one trick to do that is to hit F, click these 2 faces, edit, surface, create object, edit, surface, connect, edit, surface, create object, edit, surface. Oh, Control Z, so I went back. So I hit these 2 surfaces, hit edit, surface, create object, edit, surface, connect. Again, the same thing on this side. Surface, create object, edit, surface, connect. Okay, so now we see what this probe looks like, right? Something like that. It's somewhat more realistic, I would say. And now we need to assign a wave port on this side. Okay, how do we do that? I'll use the same trick as before. Edit surface, create object, edit surface, thicken sheet, minus 10 or maybe 5 microns. And then I'll select this sheet, and then select all faces, and then deselect the front and back face. And then say edit surface, move faces along normal. I don't know, 500 microns maybe. Okay, that's a little big, I suppose, but that's okay. The top and bottom faces don't need to be that big, so I'll select them, move them back, minus 200 microns or so. Maybe a little bit more, minus 300 microns. Okay. So now we see it looks like a nice port face. Select this face, surface, create object, assign excitation, port, wave port. Right click, assign material, and let's make this PEC. Okay. So that's it. We have our probe coming in here. It's kind of like, I mean, this is not exact model of a probe. I'll leave a link in the description, a couple of links on where you can maybe see better models, but this is a close enough model, I would say. The reason I'm doing it this way is now we can actually assign port impedance, and you can see what port impedance we're coming in with. It should be 50 ohms, right? So we have a wave port on this side, wave port on this side, and that's the transition. If you know the exact dimensions of your probe, you can make this more accurate, but this is just a starting point. So let's check our materials. We have ground plane, fine, 3 cylinders are all copper. You can make it gold if you think your probe is in gold. And so what we can do is select all this and unite all of them into just a single probe. Port cap, 2 port caps, that's good. Silicon substrate, 2 oxide layers, and the radiation box. Okay, excellent. So let's simulate this. Okay, simulation is done. So one thing I want to plot that's new is the port Z0 for the new port that we've made. And you see it's very close to 50 ohms, and that's because I've simulated this before, so I know the dimensions. And that's good. So we have 50 ohm line coming in here, and then we have these 3 pins that attach onto or that land on these pads, and then that transitions into the grounded coplanar waveguide on chip. Okay, let's compare S parameters again. So we see that compared to the previous model, it's very similar. And that's why I said that, this model is really good enough depending on what you're trying to do. So that's pretty much it. With this, I would like to conclude. So just in summary, we've made 3 different probe models. So we've made a simple model like this, where the electric field lands vertically. And we saw that it's slightly different from this model where electric field comes in horizontally and then goes maybe around this pin. And the third, probably the most accurate model, or more accurate model, I would say not most accurate, but we have a wave port that excites a mode that comes in. One thing to check for wave ports is make sure it's the right mode that's excited. So when I look at the fields of this wave port, we see that it's the right differential mode, right? Of this coplanar waveguide. And of course, if you have an actual 3D model of a probe, then you can make it more and more accurate. So there was just one more thing I wanted to check. Okay, yeah. So 3 reminders, always check materials are correct. And then check that the port field is correct. So even on this port, you should check the field and make sure it's correct, and increase the size of the port to make sure you have a converging solution. Then de-embedding, you can do de-embedding if you have experimental TRL calibration loads on the chip, or if you don't have it, then you can even use something like this maybe to model the S parameters, and then you can invert them and remove them from your measurements. Of course, you can make this more and more complicated if you know what the probe looks like. In reality, this is not what the probe looks like. It kind of extends beyond it, and then the pin kind of sticks out from the middle. And different probes have different geometries. But what I wanted to show with this is that despite the complicated geometry of a probe, the results don't change that much, especially compared to this design, which is why I prefer this in actual simulations. Okay, so what I'll actually do is I'll upload this HFSS file with all these 3 models, so you don't have to maybe go through and draw all of this again in case you want to just look at how we've set it up. Of course, going through the video is good enough, but I'll leave a link in the description to this new website that I've made where I can upload these design files that you can access easily. Okay, if you have any questions, leave it in the comments. Hope this was useful. Have a nice day. Thank you.